All right, welcome to this explainer. Today, we are going to do something pretty cool. We're setting out to completely demystify the very building blocks of math. We use numbers literally every single day, but we rarely stop to think about the invisible architecture that makes all of mathematics possible. So we're going to construct the real number system from the ground up, and I promise you, you're going to see numbers in a whole new light. But hey, before we start building, I've got to challenge a basic assumption. Is 0 a natural number? Seems like a really simple question, right? Well, the answer actually reveals a lot about how our ancestors first started using math. So just kind of keep that in the back of your mind. Oh, and here's another puzzle for you. Can a number be both rational and irrational at the exact same time? Like, is there a mathematical overlap there? Or are we talking about completely exclusive clubs? We are going to uncover that answer together very soon. And finally, think about this for a second. Why is pi considered irrational? We all know it, it's a famous number, but what exactly makes it break the rules? By the end of this explainer, the complex rules governing all these numbers are going to be crystal clear. Okay, let's dive right in. So we're kicking things off at the absolute foundation, natural numbers. These get denoted by the letter n, and these are literally just your everyday counting numbers. 1, 2, 3, 15, 100. It's math at its absolute most relatable. Whenever you count tangible things out in the real world, like counting students in a classroom or books on a shelf, you are using natural numbers. But as human civilization progressed, we realized we had a bit of a problem. How do we mathematically represent nothing? Think about it. If you have 2 apples and you give 2 away, what are you left with? That realization basically forces our whole system to evolve to include 0. When we combine our natural numbers with 0, boom, we get whole numbers, denoted by a W. So, going back to answer our earlier question, no, 0 actually isn't a natural number. It is the very start of our whole numbers. But life isn't just about having things or having nothing, right? Sometimes you owe things or things go below 0. Enter the integers, represented by a z. Integers take our whole numbers and just completely expand the universe to include negative numbers. So now we've got -5, 0, 7, 18. We have officially unlocked the ability to go backward. And this maps so perfectly to our everyday lives. Think about a freezing winter day. When the temperature drops below 0, we literally need negative numbers to describe it. Or, well, your bank account. Gains are positive integers, sure, but if you dry out more money than you actually have, those debts, those are represented by negative integers. Okay, so what happens if we want to divide these integers? Say 1 divided by 2. We get fractions. And this brings us to rational numbers, which are marked with a Q. The rule here is super simple. A rational number is basically anything that can be expressed as a fraction. A over b, where both are integers, and b is not 0. Because as we know, dividing by 0 completely breaks the universe. So 1/2, -7/4, or even just the number 5, since it's really just 5 over 1. These are all rational numbers. Now, what's really fascinating is how we spot a rational number when it's written out as a decimal, because they always follow a very strict set of rules. They either terminate, meaning they come to a nice clean end, like 0.5 or 2.75, or they repeat in a predictable pattern forever, like 0.333 or 0.121212. If a decimal does either of those two things, it is absolutely a rational number. But, well, not all numbers play nicely by these rules. Take the square root of 2. Fun fact, when mathematicians first discovered numbers like this, it literally caused a philosophical crisis. It doesn't terminate, and it doesn't repeat. It just goes on and on, totally randomly forever. And that brings us to the ultimate rebels of the math world. Irrational numbers. By definition, these are numbers that just cannot be written as a neat ratio of 2 integers. They completely defy those fraction rules we just talked about. Famous examples? You've got pi, the square root of 2, the square root of 3, and Euler's number, e. Let's just put these two cams side by side to really see it. Rational numbers are orderly, right? They terminate or they repeat. Irrational numbers, on the other hand, are chaotic. They strictly never terminate and they never repeat. Because their definitions are exact opposites, a number can literally never be both. It's mathematically impossible. They are 2 entirely separate clubs. And here it is, the climax of our structural build. When we take all those orderly rational numbers and combine them with all those chaotic irrational numbers, what do we get? The real number system, denoted by the letter R. Literally everything we've talked about so far lives inside this massive mathematical umbrella. So how do all these pieces actually fit together? Well, our hierarchy perfectly summarizes what we've just built. We started with natural numbers, right at the core, 1, 2, 3. Then we added 0 for whole numbers, added negatives for integers like -5, included fractions for rationals like 1/2 or 0.75, and then we brought in those wild irrationals on the side, like pi and the square root of 2. Every single subset has its own specific role. And you know what's really cool? The most beautiful way to visualize this entire vast family of numbers is on the number line. Every single real number corresponds to exactly one unique point on this continuous, unbroken line. It maps our integers neatly from -3 to 3. It locates our precise fractions like 1/3 or -2.7. And yes, it even places our irrational numbers. Pi is sitting perfectly right after 3, and the square root of 2 is comfortably nestled around 1.41. Every number has a home? All right, now that we have our numbers, we kind of need to know the rules of the game, right? Let's look at the properties of real numbers. First up is the commutative property. This one simply means that order doesn't matter for addition and multiplication. 8 plus 5 is exactly the same as 5 plus 8, and a times b is the same as b times a. You can commute them or just move them around, and the result is completely identical. Now, while the commutative property was all about order, the associative property is all about grouping. So whether you group a plus b together first or b plus c together first, your final sum remains exactly the same. And the exact same underlying logic applies to multiplication too. You can associate or group the numbers however you want without changing the final answer. Let's efficiently run through just a few more essential rules here. Closure just means if you add or multiply two real numbers, your answer is still a real number. You don't magically leave the system. Identity means adding 0 or multiplying by 1 just leaves your number totally unchanged. Inverse means every number has a counterpart that brings it right back to 0 or 1. And my absolute favorite, the distributive property. Multiplying a number by a group is exactly the same as doing it separately. For example, 5 times the group of 2 plus 7 is the same as 10 plus 35, giving us 45. It's just incredibly logical when you break it down. One final, completely crucial concept here is absolute value. When you think about those straight vertical lines surrounding a number, like -5, that signifies absolute value, which is simply just a number's physical distance from 0. And because distance can't be negative, the absolute value is always positive. The absolute value of -5 is just 5. And hey, this isn't just abstract math. This is highly practical in real-world error measurement and engineering tolerances, where you really only care about the size of a gap, not the direction. Okay, we have built a lot of architecture today. Let's do a really quick interactive check just to see how well these foundational blocks locked into place for you. I'm going to throw some true or false statements at you based on our hierarchy. You ready? Here's the first one, true or false. Every integer is a rational number. Take a second, think back to that hierarchy table, and it is true. Remember, an integer like -5 can easily be written as the fraction -5/1, so every single integer is safely inside the rational number club. Okay, let's flip that around. True or false? Every rational number is an integer. False. This is actually a classic trap. While integers are rational, it definitely doesn't work in reverse. A rational number like 1/2 is a fraction, and it certainly is not a whole solid integer. Last one for you. True or false? 0 is a whole number. True. This goes all the way back to the very beginning of our explainer. When we took our natural counting numbers and desperately needed a way to represent nothing, we added 0, which gave birth to the whole numbers. Well, you've successfully navigated the foundations of math today. But before we wrap, I want to leave you with a bit of a provocative challenge. We talked a lot about pi and the square root of 2, but what about the golden ratio, denoted by the Greek letter phi? Why is that irrational? This specific number mysteriously appears everywhere, in art, architecture, and even the literal spirals of nature. I challenge you to go investigate this on your own. Find out how it was discovered and see if you can uncover its secrets. Until next time, keep questioning, keep learning, and thank you so much for joining me on this explainer.